This presentation provides an overview of the work carried out during my second-year industrial engineering internship at Udayana University, Bali, Indonesia, under the supervision of Professor Tirta.nindhia. The overarching subject of this internship is the optimization of surfboard selection approached from a mechanical and industrial engineering perspective. First, this presentation is going to be about the context and the project overview. Then it will lead to the damping tests that I've done and into the surface survey and into the shop analysis to finally conclude. The central objective of this internship is to link a surfer's anthropometric profile, namely height, weight, and experience level, to the most suitable board specifications. To address this problem, three complementary approaches were conducted. First, a vibration damping characterization of two surfboards using an experimental method. Second, a survey distributed to surfers in order to collect morphological and behavioral data. Third, a structured interview with a local surf shop aimed at gathering industrial and supply chain insights. Each of these three contributions will be presented in turn. Surfboards are subjected to complex dynamic load during use, including hydrodynamic pressure from wave impact and periodic bending forces induced by the surfer's weight. One key mechanical parameter governing the structural response of a surfboard is the vibration damping ratio, denoted zeta. A board exhibiting a high damping ratio would dissipate vibrational energy rapidly following an impulse, resulting in a smooth and stable feel underfoot, which is a characteristic generally appreciated by beginner surfers. Conversely, a low damping ratio implies that more vibration is transmitted to the surfer, which tends to be preferred by experienced riders. Two polyurethane surfboards were selected for this study based on their availability at the Udayana University laboratory. Board A is a brand new kit-just-found shortboard, measuring 6 feet 3 inches in length and weighing 1.42 kilograms. Board B is a nylon R-fan board measuring 6 feet and 10 inches and weighing 3.48 kilograms. The experimental method applied is the free decay logarithmic decrement method. Vibration data were acquired using an inertial measurement unit fixed at the midpoint of each board using adhesive tape. The board was suspended from a metallic stand to approximate free boundary conditions. An impulse excitation was then applied manually at the midpoint using a small instrumented hammer. 3 independent trials were conducted per board, and the damping ratio was computed automatically by the acquisition software for each trial. Out of 6 trials conducted, 3 were retained on the basis of a validity criterion requiring the damping ratio to be strictly positive. The 3 rejected trials presented either negative or anomalously low values attributed to erroneous peak detection resulting from inconsistent manual impacts. The retained results are a mean damping ratio of 0.178 for board A and 198 for board B, representing an approximate difference of 10%. Board B exhibits slightly higher damping than board A. These results can be partially explained by the significant mass difference between the two boards. Board B being 2.45 times heavier, which combined with similar thickness lowers the natural frequency of the system and modifies the energy dissipation rate. It must, however, be acknowledged that the data set is very limited, with only 2 valid trials for board A and 1 for board B. These results are therefore indicative rather than statistically established, and a larger experimental campaign would be required for a reliable characterization. In parallel with the experimental work, a questionnaire was designed and distributed to surfers in Bali using Google Forms. The survey comprised 19 questions organized around 4 themes. The first theme covers the surfer's personal profile, including age, gender, nationality, height, weight, and body type. The second theme addresses surfing experience, including self-assessed level, surf style, and number of years practicing. The third theme focuses on the board currently used, including its length, volume, and how the surfer chose it. The fourth and final theme captures subjective satisfaction with ratings on paddling ease, stability, maneuverability, and speed. It must be noted that few responses were collected during the internship period. The results are therefore indicative and not statistically representative. Despite the limited sample size, several preliminary observations can be drawn from the responses collected. The data suggests that beginner surfers tend to use longer and higher volume boards, which is consistent with the stability requirement for learners. More experienced surfers appear to favor shorter boards and prioritize maneuverability in their satisfaction rating. Additionally, the majority of respondents indicated that their board was chosen based on advice from a shop or instructor, rather than personal technical knowledge. On this slide, you can find the satisfaction ratings about overall satisfaction, paddling ease, stability, maneuverability, speed, and if the board fits the surfer's body. It is on a scale up to 5. The third component of this internship consisted of a structured interview conducted with a local surf shop in Bali. The objective of this visit was to gather industrial and operational insights that could complement the mechanical and survey data, and to establish a connection between the engineering work carried out and a real-world surfboard retail and supply chain practices. 9 questions were prepared in advance, organized around 3 themes: board selection, criteria applied by professionals, board life cycle and maintenance practices, and local manufacturing and supply chain dynamics. 3 main insights were drawn from this interview. Regarding board selection, the shop confirmed that the 3 primary criteria used to assign a board to a student or customer are weight, height, and level. Regarding board life cycle, it was noted that boards rarely break under normal conditions and are repaired multiple times before replacement. An interesting observation is that water infiltration through small holes can progressively increase a board's mass, altering its mechanical behavior. Advanced surfers typically owned 2 or 3 boards for different styles and wave conditions. Finally, regarding the local supply chain, all boards sold in the shop are manufactured locally in Bali, and no boards are imported. The production lead time is approximately 2 weeks for shaping, followed by roughly 1 additional month of curing time for the fiberglass laminate, which is critical for mechanical integrity. Boards are ordered individually rather than in bulk, which reflects a made-to-order production model. To conclude, from a mechanical standpoint, the vibration damping characterization of 2 surfboards yields preliminary damping ratio values of 0.178 for the short board and 0.198 for the front board, establishing a first quantitative mechanical baseline. From a user standpoint, the surfer survey provided initial morphological and behavioral data, confirming the relevance of height, weight, and experience level as key selection parameters. From an industrial standpoint, the surf shop interview validated the selection criteria used by professionals and revealed important supply chain characteristics specific to the Bali market. Thank you for your attention.